4.1 is our introduction to anti-differentiation, and we have spent pretty much the entire semester up to this point evaluating derivatives, and we interpreted derivatives in various ways. For example, we said that the derivative at a point A could be the slope of the tangent line to the curve at that given point. We've also used the derivative to figure out the velocity of a particular particle based on its position equation. And we also took the derivative of the velocity function in order to determine the acceleration function. So we used the derivative in various ways. We looked at some business models and things like that along the way too. But today we're going to look at the opposite of taking the derivative. And as you know in mathematics, in order to solve equations, we need to be able to undo certain processes. For example, the opposite of adding 5 to both sides would be subtracting. The opposite of multiplying both sides by 3 would be dividing by 3. So every operation in mathematics that we've talked about over the years has an inverse, right? We know that the inverse of the exponential is, for example, the log, the natural log, for example. The antiderivative is the opposite of the derivative, and it has some very useful applications in terms of geometry and in terms of physics. And if you look at the top of page 386 here, it says, given a function y is equal to v of t, the velocity of an object at time t, we can determine an object's distance traveled over an interval of time. If we are given a function y is equal to p prime of x, the marginal profit of a business after x units have been sold, we can determine the business's total profit after x units have been sold, and so forth. In other words, whereas in the past we used the derivative to get from point A to point B, this time we're going to go from point B back to point A. Theorem 1 says that the antiderivative of f of x is the set of functions capital F of x plus c such that the derivative of capital F of x plus c is equal to f of x. The constant c is called the constant of integration. And you're probably looking at this theorem and saying, okay, this is fairly complex. But once we get into it, I think you'll see that it's a lot simpler than it appears to be at first glance. So let's take a look at that theorem in motion, so to speak, and hopefully things will become a little bit clearer. We've seen these integrands before as derivatives of other functions. In other words, if you take the derivative of 8x plus some constant, then we know that the derivative of 8x is 8. Well, if the derivative of 8x plus c is 8, then the antiderivative of 8 would have to be 8x plus c. And this is our notation for antiderivative, also known as the integral. And on part B, we know that if you take the derivative with respect to x of x cubed plus a constant, you get 3x squared. And again, this is just power rule. Well, that means that the antiderivative of 3x squared with respect to x has to be x to the power of 3 plus some constant. The constant could be 0, by the way. And so on. If you take the derivative with respect to x of e to the power of x plus a constant, you get e to the power of x. And that just means that if you take the antiderivative or the integral of e to the x with respect to x, goodness, that takes you back to e to the x plus some constant. Perhaps it would be best if I just let the author's type suffice. Let's see part D. If we take the derivative of ln x plus c, Well, we know that the derivative of ln u is just du over u, and the derivative of x is 1. So the derivative of the function is 1 over the function itself. And that means if we were to take the antiderivative of 1 over x with respect to x, then that would give us the natural log of the absolute value of x plus c. And why do we have to take the absolute value of x? Because if you recall, if you look at the function of ln x, the domain is all x values from 0 to infinity. Theorem 2, rules for antiderivatives. This is going to be the big theorem here for this section. If you want to take the integral of a constant with respect to x, then that has to be kx plus c. For example, if you have the integral of, let's say, 3 with respect to x, that would have to be 3 times x to the power of 1 plus some constant. Now, why is that? Because if you take the derivative of 3x to the power of 1, that's just 3. And of course, the derivative of a constant is 0. Notice that x to the power of 0 is the same thing as 1. So technically, we could make the case that we do have an x to the power of 0 here, but that's just 1, so we don't write that. And when we do the power rule, remember, we subtract 1 from the exponent. So when we take the antiderivative, we do the opposite of subtracting 1 from the exponent. We add 1 to the exponent. And instead of multiplying, we divide. In other words, if you take the integral of x to the power of n with respect to x, it's going to be x to the power of n, not subtracting 1, we add 1, and then instead of multiplying, we divide, and we divide by n plus 1. And we have to add that constant, typically, if it's an indefinite integral. And of course, that's the power rule, which is A2 here. The natural logarithmic rule says that if you want to integrate dx over x, it's the natural log of the absolute value of x plus c, and that's if x is greater than 0. I'm sorry. This is for any value of x, and if x is positive, you don't have to use the absolute value sign. You can leave it off because x is already positive. I tell my students that you really can't go wrong using this, using the absolute value sign. However, my math lab may balk at that some, so try it and see. And A4, the exponential rule for base e, remember that the derivative of e to the u is e to the u du. The antiderivative of e to the power of ax dx is e to the power of ax divided by a plus c. And of course, a cannot be 0, right? Because a is our denominator. We cannot divide by 0. And this is pretty much what I said earlier. The power rule for antiderivatives can be... The power rule for antiderivatives can be viewed as a two-step process. We increase the exponent by 1, and then we divide by the term, we divide the term by the new power. Whereas with the derivative, we would multiply by the existing power and then subtract 1. So it's really the very opposite of finding the derivative. And here again, they illustrate that if you have the integral of x to the power of n with respect to x, that's what the dx means here, then you simply take x to the power of n plus 1, and then you divide by n plus 1. And if it's an indefinite integral, do not forget to tack on the constant value. Let's look at a couple of examples here. Example 2. Example 2, part A says, what is the antiderivative, or what is the integral of x to the power of 7 with respect to x? And we're just going to use the power rule here. We're going to add 1 to the exponent. That gives us x to the power of 8. And then we would divide by 8. And since this is an indefinite integral, we have to add plus c. Now, just for fun, let's check to see if we did that correctly. If this is the antiderivative, let's take the derivative of 1/8 of x to the power of 8 plus a constant. Well, if you take the derivative of 1/8 x to the power of 8, that would give you 1/8 multiplied by 8x to the power of 7. And of course, the derivative of a constant is 0. And since that's 0, we'll just take that off. We typically don't have that in our response. And then we have the 8's canceling here. And we can see that when we take the derivative of the antiderivative, it takes us right back to our function. Let's look at part B. On part B, we have the integral of the square root of x with respect to x. And the trick here is to remember that the square root of x is x to the power of 1/2. So I'm going to rewrite it as such. And again, this is the integral with respect to x. And it's the same thing. Since it's the antiderivative, we have to add 1. So 1/2 plus 1 is 1/2 plus 2/2, which is 3/2. And then we have to divide by 3/2. But remember, if you divide by a fraction, it's the same thing as multiplying by its reciprocal. So instead of dividing by 3/2 and writing it that way, we'll just go ahead and multiply by 2/3, and then I have to add plus c. Now we could take the derivative of this to verify that we would actually go back to x to the power of 1/2, which is the square root of x. We're not going to do that. You might want to do that as an independent exercise, however. Let's look at part C. Without doing a lot of writing on this one, I'll just follow along with what the author has. On part C, we're given 1 over x cubed, and we need to rewrite this as x to the power of -3. Remember, if you take a positive exponent and you take it from the denominator to the numerator, or vice versa, it changes the sign of the exponent. And writing it as x to the power of -3 allows us to use the power rule. And we'll just add 1 to -3, and then we will divide by that same amount. And of course, -3 plus 1 is -2. So we're just going to change the exponent to -2. And then we have to remember to divide by -2. That's why we have the minus sign out front. And of course, we have to add the plus c. Here, the author takes the derivative of the solution and actually generates the original function, x to the power of -3, which can be rewritten as 1 over x cubed. Let's take a look at example 3. On example 3, we're taking the integral of e to the power of 4x with respect to x. And I've never taught it this way. I've never really taught this where we just simply look at the formula. And that sort of bothers me, but we'll do what the book says here. We'll just do the formula. if we take the integral of e raised to the power of ax with respect to x, that is going to be equal to 1 over a times e to the power of ax plus c. That is terrible. This is actually ax. Let me rewrite that. I hope it's better. Let's see. Okay, so this is just the formula that they gave us. And again, we're not math majors. We're not going to get into the reasoning behind this formula, so just commit it to memory or have it in your notes when you take your quizzes online and your exam. But here we have e to the power of 4x, where my a value is 4. And the recipe simply says it's going to be 1 over 4 times e to the power of 4x plus c. So that's all we really need to know. And if we take the derivative of our solution, notice that it does take us back to e to the power of 4x. Theorem 4.3, parts 1 and 2, probably nothing that's going to awe you that much, but part 1 basically says that if you have a constant times a function and you want to take the integral of that constant times the function, you can take the constant outside and then simply evaluate the integral of the function. That can be a big time saver when you're working these types of problems. This next one is basically taking the integral that's a sum of functions or a difference of functions. All this means is that you can break these up into two different parts and just evaluate the integral of each function. In other words, you can take the integral of the first function, and if you're adding, you'll just add the integral of the second function, and if you're subtracting, then you'll just subtract. So let's look at a couple of examples here. Example 4, find each antiderivative, and in this case, they want us to assume that x is positive. And anytime they want us to assume that x is positive, we typically start thinking about the natural log, right? Because the natural log function does not allow negative x values. So anytime you have a restriction on x, I typically start looking for things like square roots, but since this is calculus and we've done a lot of work with natural logs, start to consider maybe natural logs maybe coming into play. But let's look at part A here. All they did was they said, well, we're taking the integral of basically 3 functions added together. So they just used the additive rule, which is part 2 of theorem 3, and they evaluated each one separately. And by the way, after you do these for a while, you can definitely skip this step where you write it all out. And the integral of 3x to the power of 5 with respect to x ends up being 3x to the power of 6 divided by 6. And then the integral of 7x squared with respect to x. Remember, you can take the 7 to the outside and just evaluate the rest of it. And the integral of x squared with respect to x is x cubed over 3. And remember, technically we have an x to the power of 0 here next to the 8. So that would be 8 times x to the power of 1 divided by 1. And then, of course, we have to add plus c. And the rest of it is just simplifying. In other words, this 3/6 reduced down to 1/2. And then we had 7 over 3. That's basically it on the simplifying. And if you went back and took the derivative of this function here, it would take you back to here. Now let's get into part B, because remember, We didn't have to worry too much about x here. This is a polynomial. And here, this is not a polynomial. And in fact, x cannot equal 0 here, right? Because we can't divide by 0. So we know that there are restrictions on the domain. So what did they decide to do on this? The first thing they did was they looked at this as three different fractions. They looked at this as 4 divided by x plus 3x divided by x plus 2x to the power of 4 divided by x. Why? Because all of these values in the numerator are actually over x. So this is, in fact, 3 different fractions. And once they wrote those as 3 different fractions, they simplified. They kept the 4 over x because there's no way to simplify that. But luckily, we can cancel out the x's here. That leaves us a 3. And then we can take the x out of the bottom, take one of the x's out of the top, and that leaves us with x to the power of 3. All they did so far is they wrote it as 3 fractions and simplified. So basically, we are being asked to integrate this function here. And that's what they did. They simply took the original and rewrote it as the simplified version, and then they just evaluated each one separately. Notice that the integral of 4 over x with respect to x can be evaluated by first taking the 4 outside. That's that constant rule. So really you have 4 times the integral of dx over x. That's just our du over u. And remember that the integral of du over u, or in this case dx over x, is just the natural log of x. And we don't have to use the absolute value sign because we were told that x is positive. So that takes care of this first part here. Now you may be wondering, why did we not use the power rule? In other words, we have 4 over x, and that's x to the power of 1. Why didn't we just rewrite this as 4x to the power of negative 1 and then do the power rule? Well, because if you add 1 to negative 1, you get 0. And the power rule would say that we would have to divide by 0. That's unallowed. That's why we have to resort to the natural log. So how did they evaluate this part? This is just 3 times the integral with respect to x. And that's technically 3x to the power of 0. And if we add 1 to that exponent, that would give us 3x to the power of 1 over 1. That's just 3x. And then finally, we have 2x to the power of 4 divided by 4. But 2 over 4 would simplify to 1/2. And then we would add that constant on the end. And again, if you wanted to take the derivative of this, you would see that it would take us back to the top function there. So let's do that. Let's take the derivative of each piece. What would be the derivative of 4 times the natural log of x? Well, that would be 4 times the derivative of the natural log of x is just 1 over x. And the derivative of 3x is just 3. And then finally, if I take the derivative of 1/2 x to the power of 4, that would be 1/2 times 4, which is 2. X to the power of 3. And then, of course, the derivative of the constant is just 0. So let me try to fix this up a little bit here. That's a plus sign. I just made it totally worse. But you get the point, right? We'll let the author speak to us. If you take the derivative of our solution, it does take us back to that function there. Okay. At the bottom of the page, we have what is known as initial conditions. And if you take physics, if you ever take a physics class that is calculus based, you will definitely apply this a lot more. But I do want to say a couple of things here. Let's talk about the plus c. If you take a function, for example, y is equal to x squared, and you graph that function, it would look something like this. Now, it's supposed to be symmetrical, but use your imagination. That would be the graph of y equals x squared in yellow. But what if I wanted to graph y is equal to x squared plus 1? Well, then I would have to move the graph up 1 unit, right? Every point would move up. So it looks something like this. Or what if I wanted to graph y is equal to x squared minus 5? Then I would have to take the original graph and move everything down 5 units, which would make it look like this. In other words, when I add that constant, which could be positive or negative, what happens is it causes the graph to shift either up or down. And shifting the graph up or down does not change the derivative at any given point. For example, if I want to know the derivative when x is equal to 2, the slope of the tangent line here on the original would be the same as the slope of the tangent line here on the translated version and below. In other words, these would be parallel lines. In other words, the derivatives would be the same for that x value. So adding the constant does not change the derivative at any given point. And that's what they're saying here as well. Notice they're taking x squared plus 3x, and then they're subtracting 2, they're subtracting 4, they're subtracting 6, and so on. But they're trying to illustrate the fact that it doesn't change the value of the derivative at that point. So let's see what they did here. Example 5 says to find the antiderivative of 2x plus 3 with respect to x if f, capital F of 1 is equal to negative 2. Well, here they've given us some additional information. They have told us that if x is 1, the y value is negative 2 for capital F, which is the antiderivative. So what do we have here? We know that capital F of x, by our first definition, is actually the antiderivative of the function f of x. And if you take the antiderivative of the function, capital F of x is actually 2x squared over 2, which reduces to x squared. And then we have 3, the integral of 3 would be 3x plus a constant. And we know that for capital F of x, if x is 1, then capital F of 1 is negative 2. So all they did was they substituted 1 here for x, and they substituted in 1 here for x. And of course, capital F of x has to be negative 2. They gave us that information. That means that negative 2 would be equal to 1 squared plus 3 plus c. Well, this allows us to solve for c. And they end up figuring out using algebra that c has to be negative 6. Since c is negative 6, they know that the antiderivative for this particular problem is going to be x squared plus 3x minus 6. We do not have to put plus c because they gave us some initial conditions that allowed us to conclude that c is actually negative 6. So when they give you initial conditions, it gives you a lot of power. It tells you exactly what this function looks like. And in this case, it happens to be the function highlighted in red. the function highlighted in red actually goes through the point 1, -2, as you can see here. So let's apply this to some physical science here with the height of a thrown object. A rock is thrown upward with an initial velocity of 50 feet per second from 10 feet above ground, and it has a velocity modeled by the equation v of t is equal to -32t plus 50, where t is the number of seconds after the rock is released, and the velocity is in feet per second. Part A says determine a distance function h as a function of t. In this case, distance is the height of the rock. And then part B says find the height and the velocity of the rock after 3 seconds. Okay, so they gave us the velocity. And let's think back to what we did earlier in the semester. Remember, if I gave you the height equation or the position equation of an object, all you had to do was plug in t, right? The t value. For example, if let's say 5 seconds or 3 seconds, we would just plug 5 or 3 in for t, and we would know the location of the object. Now, since this is an object being thrown, they're not using s, they're using h for height. It's the same thing. But remember, if we take the derivative of the position function with respect to time, remember that gave us the velocity at time t. Well, if that's the case, then it should make sense that if we take the antiderivative of the velocity, if we were to take the antiderivative of the velocity, then that would end up taking us back to the position equation, or in this case, the height equation. So that's what we're going to do. We're going to take the velocity, we're going to take the integral of -32t, and by the way, that -32 you're going to see quite a bit when you're dealing with these types of problems, because an object tends to fall at the rate of -32 feet per second. So let's see, we have -32t plus 50. And where does the 50 come from? Well, think about it for a second. If the time is 0, right, that means the rock has not been thrown. And if you plug 0 in for t, you would end up having 50, because the rock is thrown from an initial height of, I'm sorry, I totally got sidetracked. I looked at the wrong part of the equation. 50 is actually the initial velocity. So if we plugged in 0 for t, our initial velocity would be 50. Okay. So let's take a look at this. If we were to evaluate the velocity, that would end up giving us -32t to the power of 2, because we're taking the antiderivative, and we would divide by 2, and then we would have to take the integral of a constant, in this case with respect to time, and that's going to be 50 t, and then we have to put that constant on here. And that's only temporary because we do have some initial conditions, right? But this is the general antiderivative of the velocity function. And now we know the height function. You tell me the time t and I'll tell you the height. Well, they tell us that when the time is 0, this thing is thrown from a height of 10 feet, right? It's 10 feet above ground when it's thrown. So what do? Well, we plug in 0 for t here and here, and that tells us t has to be 10 because that's the initial height above ground. So what does that mean? Well, it means that our exact height function is negative 16t squared plus 50t plus 10. So having the initial conditions is very powerful. It gives us a much more accurate depiction of what's taking place. Now, part B says find the height and the velocity of the rock after 3 seconds. Well, now that I know the exact equation, all I have to do is plug in t or substitute in 3 for t. And that tells me that after 3 seconds, the rock is 16 feet in the air. If I want to know the velocity at 3 seconds, I go back to the velocity equation and just plug in 3 or substitute 3 in for t. And the velocity after 3 seconds is negative 46 feet per second. After 3 seconds, the rock is 16 feet above the ground, but the negative velocity indicates that it is moving downward. In other words, they threw it up from a height of 10 feet. They threw it up, and 3 seconds later, it has come back down, and it is now 16 feet above ground. But since the velocity is negative, that means the slope of the tangent line, right, would be negative. That tells me that the object is traveling back down toward Earth. So that takes care of section 4.1. 4.2, this is my favorite section for the entire semester. And this has to do with the geometry that evolves when taking antiderivatives, because you can use antiderivatives to calculate area under curves, to be exact. So here we go. Antiderivatives as areas. And if we were in regular class, I would have a long drawn out story about René Descartes and how he came to some of his conclusions with algebra and geometry, and then we can get into Isaac Newton and those types of things. But since you can't see me and it's not quite as entertaining, we will go straight to example 1 here. If you look at example 1, it says Emma drives her motor scooter 15 miles per hour for an extended period of time. How far has she traveled after 1 hour? How far has she traveled between the first and second hour? How far has she traveled cumulatively over the first 2 hours? And what function f of t gives Emma's total distance traveled after t hours? Okay, so before we get into the total geometry here, I guess we're going to have to go back and think about the velocity and position functions that we used in the previous example. They tell us that Emma drives her motor scooter at 15 miles per hour. Well, that is the velocity, that is her speed. So I know that v of t is 15. That's crucial, right? V of t is 15, where V of t is in miles per hour. We graph V, noting that the graph is a horizontal line. So let's look at the graph on the right. T is time, and of course time is increasing here as Emma is riding along. And notice that if we graph her velocity, the velocity the entire time is 15 miles per hour. I guess she has cruise control and she's locked it in. Now we know that's impossible, because for her to go at 0 suddenly to 15 miles per hour, that's not really possible. But we're using sort of an algebra example here. And fortunately, we can use calculus to be a lot more exact after we get through this initial problem. But for all intents and purposes, let's just assume that even at time 0, she started off at 15 miles per hour. Okay. Notice that after 1 hour, we create a rectangle here, right? And this rectangle is keeping up with the fact that she traveled 15 miles per hour the entire time. In other words, at the very beginning, she traveled 15, and then a split second later, she traveled another 15, and basically, time just accumulates and starts to fill in this entire rectangle here. Now, I could spend all day shading this in, but instead the author has done that for us. So if we look at the area of that first rectangle, notice that the area is 15 because this is 1 times 15, right? Base times height, that gives us 15, and it represents the distance that Emma has traveled after 1 hour. Remember, if we take the integral of the velocity, that gives us the distance equation. The interesting thing here is that the area underneath the velocity equation gives us the total distance traveled. Think about that again. If we take the integral of the velocity, it gives us the position equation. But the integral also models for us the total distance traveled during that time. Part B. On part B, if we look at the area between the first and second hour, we get an area of 15 again, right? Because we've only gone over 1 hour. We still have a height that's constant, so that's going to be 1 by 15. And again, the total distance traveled between the first and second hour is also 15. Part 3 says, how far has she traveled cumulatively over the first 2 hours? Well, we know she went 15 the first hour, and she went 15 the second hour, which means that if you go from time 0 to 2, that's going to be a 2 by 15 rectangle. That means that she traveled a total distance of 30 miles. Okay. So here's what they did for part D. We set up an input-output table for the velocity, including a third column showing the distance traveled in each hour, and a fourth column showing the total accumulated or cumulative distance traveled. So let's think about that for a second. We know that during the first hour, she traveled 15 miles per hour for a total distance of 15. And then for each 1 hour span after that, traveling at that same constant velocity, she managed to travel another 15 miles. Well, this column here, it's keeping up with the total distance traveled for the entire trip. So after the first hour, she went 15. The second hour, she went 2 15s, which is 30. And then the third hour, she had gone 3 15s, which is 45. And then finally, after 4 hours, we have 4 15s, which is 60. So the accumulated distances traveled suggest that f of t is equal to 15t. That would give you Emma's total distance traveled. And that's true. 15 times t would give you the total distance traveled, because remember, distance is equal to rate times the time, and we know that the rate is 15. So you tell me how long she traveled, and I will multiply that by 15. For example, if she had only traveled 3 hours, 3 times 15, her total distance would have been 45 miles. And we have geometry and areas. Example 1 suggests that antiderivatives play a role in determining area under a graph. For linear functions, we can use geometry to find the area under the graph of a function. Two formulas with base b and height h are useful. Most of us are probably familiar with how to find the area of a rectangle, which is base times height, and finding the area of a triangle, which is 1/2 base times height. So we're going to apply the area for a triangle in example number 2, just to further illustrate what the antiderivative can do. Okay. Example 2, a toy drone flies in a straight line and its velocity t after takeoff is given by 2t, where v of t is in meters per second. Now this time, we do not have a constant function per se. In other words, we do not have a horizontal line. We actually have a line of slope 2 here, right? Because this is 2t. The derivative is 2. Okay. If we wanted to graph the velocity function, again, which is normally the x-axis is our t-axis for time, and then we can look at the velocity at any given time, and we can actually graph it. And again, it's a line of slope 2, and it's going to look like this. This is the graph of the line 2t. Because if t is 1, 2 times 1 would be 2, right? Would be on this point here. If t is 2, 2 times 2 would be 4. That would put us up here. And if t is 3, that would put us up here at 6. So we could have plotted that using a few points as well. Now let's look at the time between 0 and 1 second. Between 0 and 1 second. Well, if we go over 1 second, then that change in x is 1. And of course, 1 times 2 is 2, so we know that the height of this triangle is 2. Well, the formula for the area of a rectangle is 1/2 base times height. So that's going to be 1/2. The base is 1. That's the change in time. And notice that the height of the triangle is 2. Well, 2 times 1 is 2, and 2 divided by 2 is 1, which means that the area of our triangle is 1. The area of this shaded region here is 1. So let's look at part A before we get into the next picture here. It says to find the distance the drone has flown after 1 second. Well, remember that to find the distance flown after 1 second, we just find the area underneath the curve, underneath the velocity, along time from 0 to 1. And we found that to be 1. Which means that the drone has flown 1 meter. So finding the area underneath the line or the curve actually gives us the distance traveled. Now keep in mind the graph itself, in this particular case, happens to be the velocity. And remember, if we take the antiderivative of the velocity, it does give us the position equation as well. Let's look at part B. Part B says to find the distance the drone has flown between the 1st second and the 2nd second. And if we look between the 1st and 2nd second, this time we have the shape of a trapezoid. And you might want to go back and do a Google search, or maybe look on YouTube and review the formula for finding the area of a trapezoid. Or you could break this up into a triangle sitting on top of a rectangle, and you could find the areas that way. The more important concept at this point is to realize that the area under the curve, or the area of the trapezoid, is equivalent to the distance traveled between the first and second second. That's the main thing to realize here. And of course, if you wanted to find the cumulative distance traveled during the first 2 seconds, you would add our answer to part A to the answer on part B, and you would realize that the total area is 4. So that tells me that they got 3, right, for the area of the trapezoid. So hopefully this is making some sense to you. And I do like what the author is saying here. Examples 1 and 2 in this section suggest a pattern, and it's a very powerful pattern. The graph of a function that happens to be a constant is a horizontal line of height. The height of it happens to be k, right? The region under this graph over the integral as you go from 0 to x is a rectangle, and its area is equal to k, which is the constant height, times the time span x. If you look at the second part, notice on the second part, we had a line that's not horizontal. We had this line here. And the slope of this line happens to be m. The graph of f of x is equal to mx is a line with slope m passing through the origin. The y-intercept is 0. The region under this graph over the integral from 0 to x is a triangle, and its area is 1/2 of x, which is the base, times the height, mx. How do I know the height is mx? Because y is equal to mx, right? That's the formula here. So let's look at an example from business. Greenleaf Skateboards has the following marginal cost function for producing skateboards. For up to 50 skateboards, the cost is $40 per skateboard. For quantities from 51 to 125 skateboards, the cost drops to $30 per skateboard. And if you order more than 125 skateboards, you can pay $25 per skateboard. If X represents the number of skateboards produced, that would give us the following piecewise marginal function. Okay. So what does this mean? It means that for the first 50 skateboards, you would pay $40 per skateboard. You tell me how many skateboards you want, and I'll multiply by 40. If you decide, to give you the total cost, if you are ordering more than 50 but less than 125, I'm going to charge you 30. That would be the marginal cost. And then if you exceed 125, the marginal cost is going to be 25. And remember that the marginal cost is going to be the derivative, right? It's C prime of X, where C prime of X is the cost per skateboard in dollars. The cost per skateboard in dollars. So the question is, find the total cost of producing 150 skateboards. All right. Notice that we have a step function here because we have 3 different costs. We know that for the first 50, we pay $40. And then if we go between 50 and 125, the cost drops down to $30. And then if we go from 125 to 150 skateboards, the cost drops down to $25. Okay. So the total cost of producing 150 skateboards, we know the marginal cost, right? We know the marginal cost, but the total cost is going to be the area under the curve, right? Because if we take the antiderivative of the derivative, which is the marginal cost with respect to x, if we take the derivative of the marginal cost, it gives us the cost function, right? Plus c. Okay. Now, luckily, we don't have to worry about the plus c because we have initial conditions. We know parameters here, right? We know we're working with 0 to 50. We're working with 50 to 125, and then 125 to 150. And remember that when you take the antiderivative of the derivative, that gives you not only the position equation, it tells you distance traveled. And in this case, if you take the antiderivative of the marginal cost, it gives you the accumulated total, not of distance traveled, because it's a totally different problem, but it gives you the total accumulation of the cost, which is the area of the rectangles. So the area of this first rectangle is going to be 50 times 40. That gives us the cost of the first 50 skateboards. And then if I want to know the total cost of producing between 50 and 125, that's going to be 75 this way, multiplied by 30, that's the cost in that region. And then if I go from 125 to 150, that's going to give me 25 times 25, right? So the total cost of producing 150 skateboards, that would be the area all the way from 0 to 150, which would be the cumulative areas of those three rectangles. So the total cost of producing that many skateboards is going to be $4,875. So if you want to make 150 skateboards at these varying marginal prices, this is what you would have to pay for the cost. That's the cost to you. Okay. Riemann sums. Without going into a lot of detail, because the homework doesn't seem to really dwell too much on Riemann sums, I just want to talk about Riemann sums for a moment. Here's what Riemann figured out. Riemann figured out that if you have an area, or if you have a function, such as this one here that we have drawn, if you have a function and you would like to know the area underneath the function that is above the x-axis, he noticed that what you could do is you could just divide up the area into various rectangles. So here we have what? 1, 2, 3, 4 rectangles. And he said, well, if I could take the area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle and plus the area of the fourth rectangle, if I add the areas together, I will get pretty close to the area under the curve. But the problem with the Riemann sum is that if you don't use enough rectangles, you really have too much area. For example, notice that for the first rectangle, he neglected to figure out this area here that I'm shading in black, right? That did not get counted. But if you look over here, he went overboard. And his idea is, well, sometimes I'm going to underestimate, but sometimes I'm going to overestimate. And again, right here, he overestimated. And then over here, he underestimated. And his logic suggests that, well, if you overestimate about half the time and you underestimate about half the time, things sort of wash out. In other words, the area of the 4 rectangles in this case would be fairly accurate. So then he got this idea, well, instead of 4 rectangles, what if I used 8 rectangles? What if I doubled the number of rectangles? What if I put, say, a rectangle here? And maybe we put a rectangle here. and maybe a rectangle here. And let's say a rectangle here maybe. He came up with the idea that if he could take the area of now the 8 rectangles, right, then he would fill in some of the error along the way. And of course, he would end up underestimating at times, but imagine if you put 1 million rectangles in there. You just divided this up into 1 million rectangles. In fact, if the number of rectangles approaches infinity, wouldn't they become so slim that they would basically look like lines? And those billions of rectangles would actually fill up the entire area. So now we get into the theory of calculus, which is not the purpose of this class, but imagine if you keep adding very small rectangles in here, millions and millions of them, you fill up the entire area, and that enables you to calculate the exact area. So for Riemann's sum, just realize that to estimate the area under a curve, he used rectangles. And he was able to figure out the heights of the rectangles by plugging in the x values and so forth. And then, of course, he knew the distance traveled, right? Let's say he just used 1 unit. That would be convenient. And then he was able to estimate the area under the curves. And we can see here that mode of thinking. For example, if he wanted to know, let's say we have a function y is equal to the square root of 4 minus x squared. If we graph it, it looks like the upper quadrant of a circle. And if you wanted to know the area underneath the curve, right, all of this area here, he figured out that he could just divide this up. And in this example, we divided it up into 4 rectangles. And we just took the area of each rectangle, right? The area would be 1/2 times 2, right? That would be 1/2 times 2. So the area of this top rectangle, the far left rectangle would be 1. And then we go over another half. And then we could plug in 1/2 into the function. That would give us the height of this rectangle. So we would say the square root of 4 minus 1/2 squared. And we could calculate the heights of all of these rectangles just by plugging in the x values. Now remember, this is just an approximation because look what happens when you do the left points. Notice that you end up getting too much area, right? You got too much area there. You've got this error here, you've got this error here we don't need, and you have this error here. And as I said before, if you double the number of rectangles, the amount of error actually diminishes. So if you look at the bottom right, they went from 8 rectangles to, they went from 4 rectangles to 8 rectangles. And notice that the amount of error has been reduced, right? I'm sort of darkening in the area here with a pencil, but the error is diminished. So what if they went back and did 16 rectangles or 32 rectangles or 256 rectangles? Well, then the amount of error would almost be 0 here, and that would get us closer and closer to the area under the curve. And fortunately, we can use antiderivatives to generate the exact area under the curve. And in this case, it's pi, 3.1415, and so on. And we will definitely learn how to figure that out later in the semester, hopefully today. So let's look at example 6. Example 6 says to use 5 subintervals to approximate the area under the graph. And the graph is the function 0.1x cubed minus 2.3x squared plus 12x plus 25. And we are over the interval from 1 to 16. So here we go. This is the graph of the function right here. And we could have typed this into Desmos and we would have gotten the same picture. That's fine. So that's what the function looks like. And they want to know, what is the area underneath the function? Well, in order to estimate the area under the function, they decided to divide this up into 5 sub-intervals. So what do? Well, you have a distance here from 1 to 16. And of course, 16 minus 1 is 15. So that means that the length from here to here is 15. And if you take 15 and divide by the 5 sub-intervals, that gives you 3. That means that the width of each of your rectangles has to be 3, right? Delta x, the change in x, would be 3. So notice that for the first rectangle, we would go from x is 1 to 4. Then if you add 3 to 4, you get 7, plus 3 is 10, and then 13, and finally 16. This allows us to divide this into 5 rectangles. And what they chose to do in this problem, they chose to use left points again. That means the left points are touching the graph here, 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 and here. Since we're using left points, we have to get the heights of the rectangle, so we will plug 1 into the function. We'll plug 1 in for x. That would give us the height here, which seems to be about, I don't know, 33 maybe, 34.8. And to get the height of this rectangle, we would plug 4 in to the equation. To get the height of this one, we would plug in 7, and then we would get 10 here for the height of that rectangle. And finally, we would plug in 13. We'd plug 13 into the function to get the height of that rectangle. And of course, the bases are all 3. We made the bases all the same size, which is nice. Okay. So using the Riemann sum, all they did was they took the height of each rectangle, multiplied by 3, and then they added all of those together, and they estimated that the area under that curve from 1 to 16 is close to 405. And again, once we finish today, we will actually be able to figure out the exact area under there. Okay. Definite integrals. Here's where it gets to be interesting. With definite integrals, we definitely know our limits. We definitely know our parameters. For example, if you look at the drawing, notice that we're looking from x is a to x is b. Notice that at the bottom of the integral sign, they've used a, and at the top, they've used b. This lets the reader know how far we are traveling along the x-axis. We're going from a to b, so the distance would be b minus a. So the base here is b minus a, right? For example, if this happened to be 5 and this happened to be 1, then we would know that this is 4. We would just take b minus a. And you tell me what x is, and I will plug that into the function, and I can tell you the height of this very skinny rectangle here, very skinny rectangle. Now, the exact area is going to be the sum of all of the heights multiplied by delta x. It's going to be the sum of the products of the heights times the bases. And for us in calculus, this is all we really need to know, is that if you take the integral from your starting point A to your stopping point B, if you evaluate the integral of that function from A to B with respect to x, that will give you the area, the exact area under the curve. Now think about that. In geometry, we were limited to very convenient shapes, right? We were limited to circles, and we were limited to squares and rectangles and things like that because they are very rigid, very predictable. But if you have curves that go up and down constantly changing, let's say, it can be very difficult to find the area. And that's where calculus came into play. They started experimenting with the rectangles and then more and more rectangles. And then they were able to prove that the antiderivative actually produces the exact area if you know your bounds and you know your function. Our final example here, we finally did all of this work to simply get to this point here. Find the value of the integral from 0 to 2 for the function 3x plus 2 with respect to x. If you graph 3x plus 2, you get this red line right here. I'm tracing it here in black. That's your function. Notice that in the picture, we're going from x is 0 to 2. That's why we have 0 here at the lower limit, and we have 2 here at the upper limit. This tells the reader that we have a span of 2. Horizontal. This tells the reader what the function is, and this tells the reader that everything is with respect to x. So here's what we do. We evaluate the we evaluate the integral, and we end up getting 10, which means the area underneath that function as x goes from 0 to 2, the area of all of this is 10. Now, how did they get that? Well, they chose to divide this into a rectangle and a triangle. And they just took the area of the rectangle, which is a 2 by 2, that's 4. Then they took the area of this triangle by doing 1/2 base times the height, and they got 10. In other words, they're still showing you the geometry behind the scenes. They want you to understand that if you evaluate the integral from 0 to 2, the integral of that function with respect to x, you get the area under the curve. We still haven't learned how to do it exactly with calculus, and that is going to be the topic of our next section. So let's move into section 4.3. .3 is area and definite integrals. And I'm not going to burden you with reading all of the notation at the beginning. I do want you to understand that the fundamental theorem of calculus is arguably the most important theorem in Calculus 1. It covers a lot of information, and most of it we have already talked about. And if you look at the pictures here, we've already talked about limits as h approaches 0. And we've already come to the conclusion that if you evaluate the limit of a function as h approaches 0 of f of x plus h minus f of x over h, we've already concluded that that's the derivative. We've already learned those things. And you can see here that we're getting closer and closer to figuring out areas under curves as we move from one point on the x-axis to another. So let's take a look at Theorem 4 very quickly. Theorem 4 says, let f be a non-negative continuous function. That means the graph has to be above the x-axis. It's going from 0 to b, and let a of x be the area between the graph of f and the x-axis from 0 to x, with x being between 0 and b. then a of x is a differentiable function of x, and the derivative is f of x. That's very wordy. So let me just get into some further explanations, and then we'll look at a specific example, because the examples are actually easier to follow than all of this wording here. First, let's look at the pictures and try to understand the pictures. Notice that we have f of x. This is our function here. And as we go from 0 to a, notice that a is our base length. And the length from here to here is going to be b minus a. Well, a of a would be the area under the curve in that region. And then a of b minus a of a is going to give us the height, or excuse me, the area in the second region. Then they tell us in the second picture that if you take capital F of B minus capital F of A, that will give you the area under the curve. Okay. So just look at the pictures and sort of try to understand what they're saying. And now we're going to get into some specifics with example number 1. Example number 1 is going to take us from the abstract, which is just unknown functions, to a function that we actually know. We're looking at the function 1/5 x squared plus 3. And instead of using a and b in the abstract sense, we're actually going from 2 to 5. So we actually have concrete numbers and functions to work, a function to work with here. Here's the question. What is the area under the graph of the function as you go from 2 to 5? In other words, what is the area of this region here? So how would we set this up? Well, I'm going to cut to the chase, and I'm going to show you how to do it. What we would do is we have to set up an integral. And we know we're going from x is 2 all the way over to x is 5. So that means I have to have a 2 here at the bottom and a 5 here. So we have the integral as x goes from 2 to 5. The function is 1/5 x squared plus 3. And everything is being done with respect to x. Because what's happening is x is going from one value to another. So that's why we say with respect to x. Okay. We could follow these definitions here and get bogged down, but instead we're going to go straight to the power here. If I take 1/5 x squared and I take the integral of that, that is going to give me 1/5, because I can take the constant out, 1/5 of x to the power of 3 divided by 3, right? We add 1 to the exponent, then we divide by that number. So 1/5 x to the power of 3 over 3. Then we add the integral of 3 with respect to x, and that's going to be 3x. My writing tends to get worse as the day progresses here, so I think it's time for me to get ready to go home. So all I did was I took the antiderivative of each term. So the derivative of 1/5 x squared is 1/5 of x cubed over 3 plus the antiderivative of 3 with respect to x, which gives me 3x. And we have to keep in mind that we're working from x is 2 to x is 5. Okay. Now we have to simply evaluate capital F of 5. Minus capital F at 2. To get the exact area, I have to now go back and plug 5 into this equation here. That would give me capital F of 5. Then I subtract capital F of 2. In other words, I have to take 2 and plug it into this function, the antiderivative function. And once I subtract, I will get the exact area. That is exactly what they did in the example. Now what they did was they said, well, we know that capital F of x, the antiderivative, has to be 1/15 x cubed plus 3x plus c. They knew that because the derivative of capital F of x would have to give you 1/5 x squared plus 3. To me, that is not a fun exercise. So go ahead and do the antiderivative and then subtract the difference, f of b minus f of a. So let's look and see what they did in example 2. The same thing, right? This time we have y is equal to x squared plus 1. And we're going from x is -1 to +2. And they just want to know what is the area of this orange region here that's below the curve but yet above the x-axis. All you have to do is take the antiderivative and then subtract and plug in your bounds. In other words, you need to figure out capital F of 2 minus capital F of -1. So let's take the integral of x squared plus 1 with respect to x. This is a definite integral, and we're going from -1 to 2. And if we take the antiderivative, we get x cubed over 3. The antiderivative of 1 is x because the derivative of x is 1. Or we could say this is 1 times x to the power of 0. And of course, if we add 1 to 0, that gives us x to the power of 1 divided by 1. But we're going to evaluate as x goes from -1 to 2. So what do we do? Well, all we have to do now is figure out the antiderivative at 2. Subtract from that the antiderivative at -1. And we have the answer. And that's exactly what they did. When they plugged in capital F of 2, they got this. Then they plugged in capital F of -1 and got this. And once they crunched the numbers, they realized that the area of this region here under the curve and above the x-axis is actually 6. And this is exactly what I just did. If you look here, it says in this definition, let f be any continuous function over the interval from a to b, and capital F be any antiderivative of f, then the definite integral of f from a to b is given by the integral from a to b, f of x dx. This is equivalent to taking capital F of b minus capital F of a. This is right here, this is arguably the most important definition of the day. So let's look at a couple of examples here. We'll look at the first two, parts A and B. On part A, we're just evaluating the integral as x goes from -1 to 4. The function is x squared minus x. Notice that if you integrate x squared, you get x cubed over 3 minus, if you integrate x, you get x to the power of 2 over 2, and we have to tack on these bounds, right? That's what I did previously. We're still going from x is -1 to x is 4. Now we simply plug in to evaluate f of b minus f of a, capital F of b minus capital F of a. Well, capital F of 4 means I go and plug 4 into this equation. That's what they did here. Then I have to subtract capital F of -1. So I have to plug -1 into the antiderivative equation. And once you crunch the numbers, you realize that the grand area, or the integral from -1 to 4, is 14 1/6. Let's look at part B. On part B, we're evaluating as x goes from 0 to 2, the exponential function e to the x with respect to x. And we know that the derivative of e to the x is e to the x. So the antiderivative of e to the x is also e to the x. So when we take the antiderivative of e to the x, we get, this is our capital F of x. And again, we're going from 0 to 2, so we will put those bounds on there. And then we have to do capital F of 2 minus capital F of 0. Well, that's just going to be e of 2 minus e of 0. And any number to the power of 0 is 1. And if you subtract capital F of 2 minus capital F of 0 gives me 6.389. What does that mean? This is going to sum up everything we did today. If I graph e to the power of x, e to the power of x looks like something like this. It's an exponential function. We evaluated as x goes from 0 to 2. And finally, we get to the fundamental theorem of calculus, the fundamental theorem of integral calculus, and this sums up entirely what we've talked about today. We're not going to worry too much about the limit definition, but they just want you to realize that the limit definition can be written this way, which is a much better shorthand. And all we're doing is taking the antiderivative at B and subtracting the antiderivative at A. I will leave the rest of this for you to look at. Example 5, they just evaluated as x goes from 1 to 10. The function is 1 over x squared. It's this decreasing function here. And they just evaluated the integral, plugged in their bounds, and they figured out that the area of that region, that orange region here, is 0.9 square units. And if you would like more examples, you can take a look at the problems on page 409 and so forth. Notice that all of the problems we did, the graph is actually above the x-axis. And that was by design, because if you have an area that is below the x-axis, then you end up getting negative area. So you have to keep that in mind as you work through problems of this nature. If you wanted to know the total area, you would actually have to take the absolute value of the areas underneath the x-axis. In example 7 here sums it up entirely. We have a graph here. And notice that at times the graph is below the x-axis, sometimes it's above the x-axis, and then it's below again. And if you try to find the areas below the x-axis and above the curve, you're going to get negative area and so forth. And then they walk you through the fact that if you evaluate from -1 to 2, you end up getting a negative result, which is expected because you do have a lot of area that's underneath the graph. In other words, the cumulative area underneath the graph would be a negative number that's larger than the cumulative area above the x-axis and below the graph. The negative issue is not going to be a problem overall for the homework, and definitely not for the final exam. So I'm going to leave you at this point. Do not worry, I'm going to give you several supplemental videos that go with these exercises. This can be a very overwhelming section, especially in one lecture. So please watch the videos that I add to this lecture before you start the homework. I think you will realize that watching several more examples being worked out will help you to go through and knock out these homework exercises. Thank you.